Can you hear me, everyone? Great. So thank you all for coming. I'm Claudia Bartoli. I'm a researcher at Witnet Foundation, and today I will be talking about building an optimistic bridge with Ethereum. So this is just a 20-minute talk, so it's going to be very light and easy to get. So first of all, I will be talking about sidechains. So as you may know, more and more projects in crypto are being built as sidechains to Ethereum. This might be due to the scalability that they bring, since they offload the workload from the main chain, but as well because of the interoperability and upgradability that they bring as well, since each sidechains have their own scheme, and they can be updated by themselves, and so on. But I would like to focus on single-purpose sidechains, since these sidechains complete their task entirely in their own chain. So that brings lightness and agility to Ethereum in particular, or to any main chain, without taking any functionality and without interrupting the functionality of it. However, all the sidechains have to guarantee some security. For example, they have to guarantee that they have a secure interaction between the sidechain and the main chain. That's for sure the most important thing, since you cannot build a proper sidechain if you're not guaranteeing this. They also have to have some kind of resistance against civil attacks. And in the case the sidechain has a different consensus with the main chain, sometimes the updatability is not so obvious, so it's hard to achieve. So these sidechains must guarantee that they work fine in terms of updatability. Yeah. So in particular, I worked for Witnet, so I'll have Witnet as an example of the sidechains for working as a sidechain with a bridge to Ethereum. So I'll explain a bit what Witness is. It's a proper blockchain that works as a sidechain to Ethereum. Is incentivized by token rewards and works with a reputation system algorithm, and it's fully permissionless, so anyone can join the blockchain and can be just running a node and be part of the ecosystem. So the purpose of Witnet is to retrieve data from public APIs in the blockchain and then send that data to smart contracts in Ethereum, so that smart contracts have a view of from outside the main chain from Ethereum. So of course we needed a bridge to connect that data to Ethereum. That's why I'm giving this talk. So in this talk I'll explain just as an example of the design that we have been working on for an optimistic bridge that works with Witnet and that connects to Ethereum. So I'll be giving a brief introduction about the bridges in general, brief ideas of the design, and I'll finalize with some conclusions, as always. Right. So any bridge in any sidechain works more or less similar in this overall architecture. They all must have a smart contract, since they are connecting to Ethereum. They must have a contract rich in Solidity, but must have the functions that are needed for the communications. So, for example, in Witnet, what we need is a contract that has the data requests that are being called by Ethereum that are sent to Witnet, and that contract must have also a function to get the data from Witnet back to Ethereum. Then another important point is what we call bridge nodes. These are nodes that must have visibility of both the chains. So in this case, a view of Witnet and a view of Ethereum as well. And those bridges, those nodes are in charge of the communication. So they are like sending the information that is needed in the smart contracts to Ethereum. And when a request is solved in Witnet, they are in charge of bringing back the result to the smart contract. And so as I said, in Witnet we have a reputation system, and we work with BFT consensus. So we have a different consensus with Ethereum. So for sidechains that work like that they have a different consensus, and in particular that are not working with proof of work, they must guarantee that they have a way of verifying transactions that work fine. So it's fundamental to have something to prove that something that happened in the sidechain is being true, and it can be verified by the main chain. Right, so this is like the 3 ideas that any bridge should have. And the main challenge when building a bridge is to find a balance between these 3 things. So we have security, viability, and integrity. So regarding integrity, we have to guarantee in this case, because I'm going to be talking about an optimistic design that is kept when changing to this design. The security must be guaranteed when working with a decentralized model. And viability, you have to take in consideration as well the gas cost latency that maybe affect the design of the bridge. So what happens is that when you get, for example, more viability, then maybe you are having less security and vice versa. So the idea is you have to get the balance between these 3 things. That's the most important thing. So our approach to find that balance is to work on a design of an optimistic bridge. An optimistic verification, here I have a super simple example, is just to have some block or some transaction being proposed by a proposer, and in this proposal you add as well a stake, right? Then when something is proposed, a dispute window opens, and you have some nodes that are called fishermen that are in charge of making sure that that thing that has been proposed, in this case this block is correct. In the case that the dispute is over, the dispute period is over, and no one has challenged that dispute, the block can be considered final and is added to the smart contract and can be used. All the transactions in that block can be considered finalized. Right. In the other hand, here we have an example of a block that has been proposed. A fisherman detects that something is wrong with that block proposed, so challenges the dispute. And in the case that it was wrong, the fisherman is going to receive the stake that the proposer had. In this case, the block is not considered valid and is ignored. So this is just like the very high-level idea. So there are a few challenges when doing an optimistic design. The first of it is to find the mechanism for proving frauds that work better for each design, each project. In our case, we wanted to work with an interactive dispute mechanism because after doing some research was what worked better for us. And what is this interactive dispute mechanism looks like? Well, it's quite simple. We have a reporter that is going to report, let's say, a transaction. The reporter puts some stakes on, and a dispute opens. So this column in gray is the dispute period that's been opening. Then we have the fisherman, that in the case that it detects that the transaction is not correct, will challenge and open a second dispute period. Okay, this is like the green or blue. I don't know. And in this mechanism, what is different is that the fisherman is going to put some stake as well. So the reporter, during the second period of dispute, must provide a proof of inclusion of the transaction that proposed at the first place. So in the case that the reporter is able to prove that the transaction was valid, then the stake from the fisherman will be received by the reporter. In this case, of course, the transaction is just confirmed since the reporter just proved it, no? Using the POI, that's the proof of inclusion of the transaction. So this was just an example. Of course, we have different scenarios in in this interactive mechanism, we have, it could happen that there were no disputes, so just in the first period of dispute, when it finishes, it's considered valid and finished, as in the first example. Maybe it could happen that the proposal was challenged by the fisherman, but there was no proof of inclusion provided. So in that case, maybe the transaction was not correct or even was not even existing. And in that case, of course, was the stake from the reporter that goes to the fisherman. And for the case in which more than one fisherman challenged the dispute, in this design, it's a non-problem, since just the first fisherman who is disputing and challenging is the one who's taking the reward and the responsibility of it. Okay, well, another challenge, the first one was selecting the proving frauds mechanism. Another one is to have the right rewards and the right stakes and the right latency, of course. These are three super important things that guarantee the security and the viability, well, the balance that I talked about before. And you have to be quite sure about what you're doing with these things. So in our case, with the interactive dispute mechanism, what we had is that both reporter and fisherman are putting some stake. So these stakes must be greater than the cost of the verification, because the idea is that with that stake, they are assuming the gas costs of the verifications. And of course, stake one, so the stake from the reporter must be greater than the stake of the fisherman. So apart from covering the cost of the verification, they have to become a real incentive for the fisherman. And then regarding the latency, in this design, we had two dispute periods, but both of them were bounded, so the latency is guaranteed. And just depending on each sidechain, it may be more or less, but the latency itself is guaranteed since both are bounded. And of course, if at some point you need verification instantaneously, you can just do the proof of inclusion and assuming the gas cost, and you'll get the verification of the transactions, and that will be it. And so, another challenge, and that's like the third and last of like this simplified version of an optimistic design, is regarding the verifications. As I told you before, for the sidechains that have different consensus with the main chain, you have to guarantee that the verification works. So something that has been verified in the sidechains can be proven by the main chain. So in our case, we have to focus on two things. We had to think about how do we select the bridge nodes, the nodes in charge of that communication, so they have to be working and having vision of both Witnet and Ethereum. And then you also have to look for the verification itself. So in our case, since the idea is to have a committee of several bridge nodes, we decided to work with BLS verifications that are kind of verifications that work very nicely with when you have to verify multiple signatures. Right, this is maybe a scary slide since it has a lot of maths behind, but I'll try to explain it like super simple, in a simple way. The idea of BLS, as I just said, is to verify several signatures with just one verification. So we have a sum, we consider a sum of public keys, that's the P. We consider a sum of signatures with corresponding to that public key, of course. We call them S. And then we consider, let's say, the sum of the messages. Here is actually the hash of the sum of the messages, but yeah, the idea is very simple. So you use elliptic curves, and you use the generator. So here, I don't know if this, well, I don't know, like there, you have the verification in the case of one signature, right? So you're using the generator of the elliptic curve. When you're using BLS, the idea is you can verify some of the signatures using these functions that are called pairing functions. They are really nice functions that work, as I said, with elliptic curves. They are binary functions, and well, I'm not going to be talking about that, but the idea is using that, you can verify the sum of the signatures, and by verifying the sum of the signatures, you're verifying each of them. So how do we use it? Well, the idea is you have some bridge nodes that are voting and proposing, and you have their signatures. So you consider the sum of the signatures, and you just, by applying BLS with one verification, you will get the verification of all the signatures that you need, and then you can apply consensus in the case that they agree on the verification and so on. So they are quite nice, even if a bit complex. So, right. So just explain a bit what the design of the optimistic bridge in WITNET could look like. And to sum up, just going back to the balance that we were looking for regarding security, viability, and integrity. We have that the security is provided by the proof of inclusion functions and the use of BLS verifications. We have integrity that is given by the fishermen incentives. So as far as you have good incentives, you have fishermen, and if you have fishermen, you can trust the optimistic design. And then you have viability. So as I said, we only have 2 dispute periods, and these periods are bounded. So the latency is guaranteed. In our case, well, it works pretty fine. And of course, depends on the projects and so on, but I think it's a good way. And just to finish, in the end, this design in WITNET to connect Ethereum, we came up saving some gas cost up to 40%, since with this design, what you do is you avoid to do some verifications, and that verifications, in case that they are needed, are provided by the stakes, both of the reporter or the fisherman. The latency, in our case, is around 15 minutes, because we work with BFT consensus, and we have what we call super blocks, are basically like every 10 blocks we have another verification that is made. So that takes, we can consider 2 super epochs, that's what we call them, and that would be around 15 minutes. And regarding the consensus verification, as I just said, we are based on BLS verifications. So that's how we work. We select a committee of bridge nodes, and then using these verifications, we manage to use just one verification to prove all the signatures. So, well, just to go back to the idea of what this bridge does is was just in WITNET doing this optimistic design. What provides is that the data that is retrieved by WITNET through data requests and some committees and so on, that the data is taken from public APIs is sent it to Ethereum smart contracts. So the smart contracts have a view of data outside Ethereum. And that was it. Thank you very much for attending the conference. I hope to see you. I don't know if you're staying, but from tomorrow we'll be in the hackathon of Kleros, and it starts tomorrow, and it's all the weekend on. So thank you very much. I don't know if you have any question.
So I have sort of 3 questions, I think. So the first is for BLS multi-signature. So you have to encode the set of signers in the first transaction, right?
Sorry, I know yours was a question about BLS, but
to have a provable claim, you need to encode the set of signers in the first transaction.
Okay.
So do you do a bit field that work? And what do you do about the public keys? Do you put hash of public keys on chain or all the public keys on chain?
Well, we have the public keys because they are from a select committee that come from what we call ARS. It's an active reputation set of nodes that work like honestly on the blockchain, and then we know their public key, and we have them. And the idea is because of the interactive mechanism. They are the ones providing the public keys and the signatures. So they are the ones.
Yeah, but what do you store on the Ethereum chain, on the main chain? Does the main chain have all the public keys? Or a hash of the public keys?
No. It's just you prove from Witnet using a library of BLS in Solidity. You prove the.
You need the public keys.
Yeah, of course.
How do you get?
I know you are providing the public keys.
So do you keep a hash of the public keys on Ethereum?
No, you don't. You just
keys?
provide. I mean, you can prove something like just giving the public keys and the signatures. Like I'm going to prove you this. It's not that you need to have them.
So what? Yeah. What does it? So on Ethereum you have to store something for the public keys. So are you proving from the Witnet state that these are the public keys? And then have to include the public keys in your challenge transaction.
Yeah, I mean the smart contract that we work with, like the in the bridge, must have like is in. I mean, it has is in touch with Witnet, so it knows the public key is needed and the.
So you do a light client proof.
So we have them in. Sorry.
So do you store the public keys, or does that mean you have a light client proof from the previous Witnet state that these are the public keys?
I think, in each superblock you present, when a superblock is finalized, right, you have like the committee that was signing that superblock, and in that superblock you have the public keys that were signing.
Right, so you would have to prove them in. But for the original transaction, you still need to have some commitment to the set of people who signed, right?
Sorry? Again?
For the original transaction, in order to challenge it, you have to have a deterministic thing, so you need to know who signed it.
That's why we have an interactive mechanism. So you just, you see if maybe the block is not a correct one, so you challenge that dispute.
But in order to have such a mechanism, you need to know that the original thing was wrong.
Yeah, well, not the signature, but what they are proposing.
So for BLS, if you know the public keys, if you know the set of people who signed and the signature, which is small, then that's enough. But if you don't, then maybe the fisherman is risking losing their money because they don't know that this thing wasn't signed. I mean,
they are signing what they are proposing. If they are signing something else, it doesn't matter what it's going to be valid is not what they are signing, but what they're proposing.
Well, they may be wrong because maybe all the validators were cheating and signed two things, which is why you'd want something which is for which they know that this claim is wrong. For instance, that the BLS signatures from these guys adds up to this, which you could put with just a bit field and a signature.
But how could it be wrong?
Okay, and then the final question I have is about gas costs.
Okay.
So if the fisherman you need the fisherman and the original proposer to put up more stake than the cost to verify, but this depends on the gas cost.
Yes.
So you need to make an assumption about sort of what the maximum gas cost is.
Yes.
And then there's the next question, which is you need to model how expensive it is to push the gas cost stuff up in Ethereum for the challenge period.
Yeah, I know. I mean, in our contract, we have a function that is to get an idea of what the gas cost could be. And of course, we consider like a high gas cost in order that is enough the stake that they are putting on.
Because, FOMO 3D proved that Ethereum is sensible if you pay enough.
Yeah, I mean, you have to pay enough, of course.
So you need a model of the gas cost.
Yeah, I mean, you can call a function in our contract that is going to tell you if the stake you are putting on is enough or not. Is there any other question? Okay, well, if you have any other question, we'll be in the booth in the first floor, so thank you very much for coming. Bye.